Don't look behind you, because somewhere behind your chair, an invisible boundary may already be moving through the room. You would not see it. You would not feel it. Your phone would still work. The lights would remain on, and every instrument around you would insist that nothing had changed. Yet, according to the deepest rules of general relativity, you could already be trapped inside a region from which no signal, not even light, will ever escape. It sounds impossible. Black holes are supposed to be distant objects, dark, violent monsters hidden among the stars. As long as we stay away from them, we should be safe. But that comforting idea hides one of the strangest truths in modern physics. An event horizon may begin forming before the collapse that produces it appears to be complete. Imagine that you are piloting a spacecraft near a black hole. Your ship possesses impossibly powerful engines, allowing you to hover just outside the point of no return. Ahead of you is a dark circular shadow surrounded by glowing superheated gas. You stop as close as you dare, perhaps only a few feet beyond the boundary. One push of the controls, and you believe you can still accelerate away. Then something changes. A massive shell of matter falls toward the black hole. As the black hole gains mass, its gravitational reach grows. The boundary expands outward and eventually surrounds your spacecraft. From your perspective, the explanation seems simple. You were safe. More matter arrived, the black hole grew, and then it swallowed you. But the mathematics of general relativity tells a more disturbing story. The true event horizon is not simply the dark surface you see at one particular moment. It is defined by escape. If a beam of light emitted from your location can eventually reach the distant universe, you are outside. If that light can never escape, no matter how long it travels, you are inside. When the incoming matter causes the horizon to grow, even light emitted before that matter arrives may fail to outrun the expanding gravitational boundary. Looking at the entire future of the spacetime, physicists may conclude that your spacecraft was already inside the final event horizon before the falling matter reached the old one. Nothing traveled backward through time. The future did not send a warning into the past. Instead, the event horizon was defined using information about the spacetime's complete history. To know its exact location at this moment, you must know what will happen later. An even cleaner version of this puzzle appears in an idealized solution known as Vaidya spacetime, named after physicist P.C. Vaidya. Imagine an enormous spherical shell made from inward-moving radiation. At first, the shell is vast, and the region at its center appears calm and nearly empty. You are floating at that center, while the luminous shell collapses toward you from every direction. No solid black hole has appeared. No nearby instrument detects a point of infinite density. So you transmit a pulse of light outward, expecting it to pass through the shrinking shell and escape into space. But in the mathematical model, there comes a moment when escape is already impossible. The event horizon begins at the center and expands outward through a region that may still appear locally ordinary. Eventually, it meets the collapsing shell. Only later does the violent concentration of energy become obvious. Your light signal never reaches the distant universe. It spends its entire existence pursuing a boundary it cannot cross. The prison, in a sense, appears before the walls arrive. This does not mean an event horizon physically predicts the future. It means an event horizon is a global feature of spacetime. You cannot always locate it using a nearby camera, a gravity sensor, or a single snapshot. Its existence depends on where light will end up across the entire future. This is also why three commonly confused ideas must be separated. The dark region in an event horizon. Telescope image is the black hole's shadow, created by captured and strongly bent light. It is not a direct photograph of the event horizon itself. An apparent horizon is a more local, time-dependent surface where outward-directed light rays temporarily stop expanding. Its position can depend on how space-time is divided into moments. The event horizon is different. It is the ultimate causal boundary separating light that can reach the distant future from light that never will. Physicists express this using the intimidating phrase, the boundary of the causal, past a future null infinity. In plain English, imagine following every possible beam of light through the entire future of the universe. Some rays eventually escape arbitrarily far away. Others remain trapped forever. The event horizon is the boundary between those two fates. This global character is sometimes called the teleological nature of an event horizon. The word comes from the Greek concept of an end or final outcome. It does not imply destiny, consciousness, or genuine backward causation. It means that the horizon's present location can only be determined once the final outcome of the spacetime is known. Now consider the most unsettling version of the thought experiment. Imagine a carefully constructed universe in which our entire region of space is destined to collapse billions of years from now. If every future path taken by light from this room ultimately ends inside that collapse, then the global event horizon could already extend through the room today. You would feel no wall passing through your body. There would be no flash, no sound, and no sudden gravitational attack. Locally, everything might remain completely normal. This is not a prediction about Earth or the Milky Way. It is an extreme thought experiment showing the difference between what we can measure now and what the complete geometry of space-time may ultimately reveal. That is the real horror of an event horizon. It is not merely a dark surface surrounding a cosmic monster. It is a boundary written across space and time, a line whose true position may remain unknowable until the universe reveals its final page. We like to imagine that the present tells us whether we are free. General relativity answers with a colder possibility. Sometimes only the future can confirm whether escape was ever possible. So tonight, when you turn off the lights and look toward the stars, ask yourself one question. Is the light leaving your room truly escaping into the universe? Or is it already running inside a prison whose walls have not yet arrived? If your mind is still functioning, leave your space-time coordinates in the comments. And subscribe to Cosmic Theory Lab, where the universe is always stranger than it first appears.